We are going to talk about fuzzing, reversing, and mass. This is our agenda and the topics that we are going to talk about during this presentation. So first of all, who we are. As I was saying, my name is Josep P. I'm a penetration tester and security researcher at Deloitte and Bugru Offensive Security. I'm also a product geek, of course, and here we have my blog, Twitter account, and email account if you want to contact me.
Hello, my name is Pedro Guillem. I'm penetration tester and security researcher at Telefónica. I'm interested in security since I was young, and this is our blog, my email, if you want to contact me.
Okay, what this talk is about? This talk is about our research in backup servers. And why backup servers? Well, because we think they are critical for companies, backup servers and backup clients, because if you hack or compromise our backup server or several backup clients, you could compromise an entire company. Also because they are sold as a security software, so they should be secure, right? But as you probably know, and as you will see during this presentation, they are not secure at all. Then we started to use this backup server list in Wikipedia, as you can see on the right, where we can find a lot of different backup products from different vendors. And we found several vulnerabilities in a lot of backup applications. Here we are going to talk about the retrospect application, the nodes of Handy Backup, but of course we found a lot of issues in other products, but we won't talk about them because we don't have enough time and because of legal issues as well. But the important thing here is that using these techniques that we are going to talk about here, you will find vulnerabilities in a lot of backup products, and this is for sure, okay? So let's start the zero-day party. There are no fixes for these vulnerabilities. That's why, because vendors didn't try to contact us, so it's the same. We want to show you how we found these kind of issues step by step, and then you will find more in other products for sure, other backup products at least. And we know that all of you are good people and won't use these issues with evil intent, and of course we won't be responsible of your evil ideas.
Okay, the first software that we're going to talk about is Dan Retrospect Backup Server. It's a backup client server widely used in NASA, as you can see in its own web page. We have to tell that ANC told 1 month ago that Retrospect was sold in 2012, as you can see in the copyright. In the past, one found some vulnerabilities, memory corruption and stuff, but no more vulnerabilities were reported since 2008. So this is the year without report any vulnerability. So in the one opinion is so much time. Our first step in the research will be intercept all the requests and response using Canopy. But what is Canopy? Okay, it's an amazing tool, and you can see that the Procify software and Canopy, we can intercept and play with almost anything. Okay, in the screenshot on the left, you can see the Procify software, and on the right, you can see the Canopy log. Mainly, you have a server and a client. Retrospect.exe is the server, retroclient.exe is the client, and during the client installation, you have to set a password, and when the server tries to connect to a new client, it shows this message box. Okay, and this is the screen that Canopy shows. Okay, so we know that the clients have to send to the password to the server. Why? Because if you enter an invalid password in the message box at the server, it won't send any packet. So the server now has the password and it's checking it by itself. But when the client is in the password, okay, you look this carefully this screenshot. When the client tries to the server, okay, try to add, it shows contains the client hostname, this case is Tebo, and the client version, in this case 8.5.0 and stuff. Is this another packet that the client sent to the server? And it should like that the password is in this encrypted packet inside it. Inspecting with Canopy, we realized that these bytes, DA and DA, okay, this stuff, are likely protocol headers. So we are going to do some protocol reversing in order to understand how this works.
Okay. In this case, we use breakpoints in the RigV and SendV functions, and then go further in the debugger. It's a typical way to do protocol reversing. As you can see here in the left, we have the encrypted packet in the Canopy log. And here we have in the debugger when the function recv is called, and then if we look at the buffer, we will be able to see the encrypted packet in the memory dump, as you can see here. Okay, and here we have the protocol headers and the encrypted packet. So as I was saying, using hardware breakpoints, we can find the functions which handle the socket we are looking at. For example, in the encrypted packet here, in the first byte, if we set a hardware breakpoint in the AA byte, when any instruction will try to read or write in this byte, the debugger will stop and we will be able to see what is going on. And doing this, we found this interesting function, which decrypts the encrypted packet, doing some extra operations. And here we have the decrypted packet, okay, in the memory dump. So our main goal here right now is where is the password in this decrypted packet now. As you can see here, we were doing several tests with the password test and the password test 1, and we realized that it's a password hash. Okay, it's a 4 bytes password hash. So if we are able to decrypt this packet using an exploit and get the hash, we will have a vulnerability. It won't be a really big vulnerability yet, but at least it's a good point to start. So we need some time to think and reverse the whole process here. And then we found 3 important functions here, and let's start to talk about these functions. Now, our main goal here is how is the hash packet decrypted? Because we want to write an exploit in order to get the hash of any client in this software. Then we found this function, the function 1, and using some logical operations such as shift left, shift right, and or, and so on, it will calculate 4 bytes using as a parameter the following 32 bytes key. This is the 32 bytes key. And this key is the client version plus the client hostname plus a static key. Remember that the client version and the client hostname, we got this information from the client, and the static key, we found it in the debugger as a constant, as you can see here. It's a 32 bytes constant, and it's always the same. There is another function, the function 2, as you can see here, the code. It has several loops, and with the 4 bytes from function 1 as an argument, it will generate a 1024-byte array, as you can see here in the memory dump. Then there is another function, the function 3, and with the last array from function 2 as an argument, it will create another array of 1024-byte array, doing some extra operations between the last array from function 2 and the circuit key. Remember that the circuit key was the client version plus the client hostname plus the static key. Then the function 1, it will be called again and doing the same logical operations, and using as an argument the last array from function 3, it will generate another 4 bytes. Then the function 2, it will be called again, and with the last 4 bytes from function 1, it will generate another array. And finally, the function 3, doing some extra operations between the last array from function 2 and the encrypted packet, it will decrypt the packet. Okay? So as a summary, here we have this graph. It's pretty simple. We have 3 functions, and they will be called twice. And the only really important thing that we really need here for our exploit is the secret key.
Okay, as a summary, every argument in this function is static except the key. Remember that the key is composed with the client version, this, and the client hostname, and the static key that we found in the debugger. So we have everything. We can write an exploit in order to get the hash. We will try and write an exploit in order to get the hash password from any client. So we just need to secure the function 1, 2, and 3, and use the static parameters. Okay, how it works? Look at that. This is the first packet that we have to send, and then the client responds with the client hostname and the client version. After that, we have to send this another pin packet, and this responds with this packet that contains the hash. So we are going to put all the things together in a Python exploit. This is a Python code. It's a representation of the assembly code. In Python, this is function 1. This is function 2. It's another Python representation of the assembly code of the function 2, of course. And this is the function 3, okay? This is another Python code of the assembly code. First of all, we have to show some requirements. We don't need mine in the middle. We just need to send the packet to the client. Then we have to send another packet and execute the function. And finally, we get the hash of any client. We're going to see in a demo. Okay, this is the code. This is the software, retrospect, and we're going to secure the exploit. Okay, and this is the key. And this is the encrypted packet, and this is the 4 bytes that the function 1 will create. I'll go a bit faster, okay. This is the first packet, and then give us the client hostname and the client version. After that, this is another pin packet. Give us another packet that contains the hash. And finally, our script have to go. Okay, this is the decrypted packet, and inside it you can get this hash. Okay, in this case, this is the hash.
So now we have the ability to get the hash of any client, okay? But what can we do with this hash? As you can see here, we have the hash of the password test and the hash of the password test 1. It's always 4 bytes hash, and it changes at all, as you can see here. So it's a 4 bytes hash, so we have 4 billion of possible unique passwords. And the max length of the retrospect password application is 31 characters, and we can use more or less 90 possible characters in this password. So this is the number of the possible passwords in the application, which is really big. And take into account this number and the 4 bytes hash, the collision number is this one, which is really, really big as well. It's even more than atoms on Earth, so it's really big. And as you probably could be thinking right now, yes, this is an issue or a vulnerability, but of course we will try to go further in this. Then we found the hash function, which is the function 1. We know more or less some details about this function, but we'll try to explain more details about this function during the following slides. This function will take as an argument the clear text password, which is in this case is test, okay? And it will do some logical operations such as shift left, shift right, and or then it will multiply. It will do a multiplication of the character of the password by itself, and then it will do an XOR operation. And when the function is executed, it will generate the hash of the password, as you can see here in the EAS register. So with this, how can we find a vulnerability here, and how can we exploit this? Well, in order to do that, we need to use some math. Here you have the function 1 in C code, which is easier for us to understand, and we have to look carefully at line 5 and at line 7. In line 7, we have the XOR operation of the multiplication of the character of the password by itself. We'll talk about this operation later. But now we have to focus on line 5, where we have the shift left operation, the OR operation, the shift right operation, and the AND3 operation. Here, the AND3 operation, we think that the developers try to use this AND as a mask in order to protect the bits during the rotation. But as you probably know, 3 in binary is 0, 1, 1, and any AND operation with 0, in the result, you will have a 0. And that's why this is a failure. Because if you want to protect all the bits during the rotation, in this particular case, the mask should be 7, because 7 is 1, 1, 1, there is no 0, and you will have a 0 in the result. You have this other graph, where we have the 32 bits of the hash, or the 32 bits of the result variable in this code, before the rotation. And because of how the bit rotation works, and the most important thing, because of the AND3, remember the 0 thing, in the first iteration of the loop, the bit 2 will be erased, okay? And then the bit 5, and then the bit 11, and so on. And that's why we can build a password which shares the same hash in an easy way. Okay, here we have this graph. This graph, we are going to use this graph in order to exploit and explain how it works. Here we have, well, and this graph, sorry, represents how the bits are erased in function 1. Here we have the 32 bits of the hash, and remember that we have the hash. We have the ability to get the hash of any client, so we have to get the hash of any client, so we have the bits. And here we have the max length of the password in the application, which is 31 characters. So I was saying we will try to generate a 31 length password which shares the same hash. If you remember, in function 1, we have this another operation, the XOR, of the multiplication of the character of the password by itself. And that's why we will use characters 2 and 3 for our new password, because characters 2 and 3 in hexadecimal multiplied by themselves will have these binary numbers. And we will use the third lowest bit in these binary numbers. Let's see how it works. For example, if we have a 0 in this hash bit, in this particular case, if we want to start from the last character of the password, the number 30, we'll have to use one of these two binary numbers, starting from here, from the lowest bit, and we'll have, in this particular case, we'll have to put the same bit in the black square that we have in the hash bit. So in this case, it's 0, we'll use the character 3, and now we are sharing the hash bit in this case. In the following characters, we'll use the same logic, but also we have to take into account the XOR operation. For example, if we have here a 1 in this hash bit, we'll have to put in this black square a bit with which doing an XOR operation between this bit and all the bits which are below at the same column. The result has to be the same as this one. For example, here, if we put a 0, XOR between 0 and 1, the result will be 1. So now here we are sharing the hash bit as well. And in the following characters, we will use the same logic, taking into account the XOR operation of this bit and all the bits which are below in the same column, and again and again. And in the last case, for character 0, we'll use another new logic because we have to fix or put 2 bits. And that's why, because if you remember, we have 32 hash bits and 31 characters in the password. So because of that difference, that's why we have to put 2 bits. And also, we'll use characters in this case, 2, 3, 4, and 6, because using those characters, we will have all the possible combinations in the binary numbers. For example, if we have a 1 and a 0 here, we'll have to start from here, from the lowest bit, like always, and we'll have to put in the black square a bit which doing an XOR operation between this bit and all the bits which are below at the same column. As you can see here in this red line, the result has to be the same as this one, and here the same. And putting all this logic together in an algorithm, we will be able to build a password which shares the same hash in an easy way. This is the code. It's pretty simple. We are using characters 2 and 3, and characters 2, 3, and 4 for the last case, the character 0. But the best way to show you how it works is a demonstration video. But first of all, like always, requirements, we don't need my middle, as you know. We just need the hash, which we got from exploit 1, and we will build a password which shares the same hash. And we will use the retrospect server, the trial version, which is free, and try to access to the client. Let's see how it works. Okay, here we have the server. We are adding the client in the IP69. And the client is asking for the password. This is the traffic between the client and the server. And now, just as a proof, we'll use the password test, which is the actual password of the client, just as a proof. We copy, we paste it here, click OK. And here we have the traffic between the client and the server. As you can see, there are a lot of encrypted packets. We'll talk about these encrypted packets later. And here we have the control panel of the client. We can click at Tools, and everything is working. That's OK. Now we will delete the client, and we will add it again in the same IP address, IP69. Again, the client is asking for the password, and now we'll use our exploit. We'll use this function in order to calculate the hash of the password test, just as a proof, but remember that we have the ability to get the hash of any client. And we will pass the hash to this binary, and the binary will give us a password, a 31-length password, which shares the same hash. As you can see here. Okay. We copy here. As a proof, here we have the password. Paste it here. Okay, now here we have the control panel of the client, but if we look carefully at the canopy log, we can see that the server is trying to send an encrypted packet to the client, and the client is not responding, so something is not going well here. And if we click Add Tools in the control panel of the client, we will have this network error, so definitely something is not going well here. We'll see why.
Okay, so to respect the .tcr of the client, use an encrypted protocol between them. This is the request response. So we start to think that the encryption is using the plaintext password as the key. As a few test application, you can change the password of the client. Okay, doing some test, we realize that the client has to send all the information to the server in order that the server has to know the password. Using several tests, finally, these two passwords, okay, this is a password that we built, has the same hash, as you can see in these screens, but has these 4 bytes that are completely different. So we know that in the installation of the client, we have to set the password. So we're going to check with the Linux client and do the installation. And first of all, we have to disassemble the main function. And we realize, so we see this function, subset for access password. That could be interesting because it's we call the first time that we going to change the password. And following this function, we realize that will be called this another function, create hash block, create set key, and create to encrypt. So we are going to see what is this function, okay? Create hash blocks is the function 1. Remember function 1 with the ANS3 operation, ANSIF write, and so on. The create set key, we realize that is the function 2 with many loops. And the create to encrypt is the function 3 with the extra operation, the array, and so on. So it looks like that the encrypted packet are generated somehow with the plaintext password using our famous function 1, 2, and 3. So we need to find how these magic bytes are generated. We make a test, okay, a test with the password test. We are going to see with yourself how these 4 magic bytes will be generated using MyDA Pro and GDB server. Sorry.
Okay. Here we have the IDA Pro. We are using the debugger of IDA Pro. We have attached the Linux client using GDB server, the Linux retrospect client. The client is asking for the first access password. And of course, we typed the test password. And the function 1, it will be called and using as an argument, as you can see here, in the clear text password in the memory dump. Then, when it's executed, it will generate the hash of the password. This is not new for us. And then the function 2, it will be executed and using as an argument the hash of the password, as you can see here in the memory dump. Again, this is not new for us. It will generate the 1024-byte array. And then the function 3, which is called create to encrypt. Using as an argument the last array from function 2 and the clear text password, and this is new for us, okay, and it's important, we'll see why. It will generate another 1024-byte array. And finally, the function 3, which is the function 1 again, sorry, the crypt hash block. It will be executed using as an argument the last array from function 3. And when it's executed, it will generate this interesting four magic bytes, the 18DT5744. So the four magic bytes are generated with the hash and the plaintext password. We have the hash, but we don't have the plaintext password. Remember that we have the ability to get the hash of any client, and we have the ability to build passwords which share the same hash, but we don't have the plaintext password, the actual password of the client. So at this point, we thought that it was pretty difficult to get something good here, but let's do some maths again, just in case.
Okay, maths. The 4 magic bytes were generated from the password and the hash. This is the graph that somehow how the 4 magic bytes will be generated. The important thing is there it has the array 2 will be created. It's using the password in clear test and the array 1. And the array 1 is will be created using the hash. And the hash is known to us, for the array 1 is known to us. So it's a static value for us. Password clear test always sort with 1024 bytes array using this formula. This formula is the formula I have to use in order to create the array 2. Function 1 erases a lot of bits, as you know. As a consequence of this, it's only important the 32 bytes of the array 1. But why the last 32 bytes of the array 1? Okay, you look carefully at this graph. This graph represents the way that the bits will be raised. The gray area is the area where the bits will be raised. So it's only important the 992 until 1023. Actually, this is the last 32 bytes of the array. So these bytes will be used in the third line of the formula because it's between I and 1024. As array 1 is static because it's known to us the hash, okay? We only have to take care of this part of the formula, okay? And actually this part is the sort of all of characters of the password. Let's go on to see an example, okay? This is the password test, and this is the hexadecimal value of the password test. If you sort all of these characters between them, we get this number 16. So the trick will be to get a password which says the same hash, and also if you sort all of these characters between them, we get the same number, okay? So as we have to sort only printable characters from 20 to 7F, we get 127 characters. So you only have to brute force the 128 possibilities. This is the password that we are going to create. So we only have to pick up, okay, because if you sort all of the characters between them, we get 0, 1, 2. And in this case, in the case of test, we only have to take care of this number, okay, number 16. This is the algorithm that could make it possible. It uses recursivity techniques. Just for you.
Okay, again, the exploit 3, the requirements, we don't need, again, mine in the middle. We just need the hash, which we got from exploit 1. We will build a password which shares the same hash and the same 4 magic bytes. And again, we will use the Express server, the trial version. Let's see how it works. Okay, here we have our binary, super hash binary, and we will give to this binary the hash of the password, and the binary will give us all the 128 possible passwords. Now, we will add the client again, and here we are using the password test, which is the actual password of the client, again as a proof. Click OK, and here you have the control panel of the client. We can click Add Tools. It's working. That's OK. So now, adding the client again, and now we will use our first password from our exploit. Here we have the password. Copy the password, paste it here, click OK, and now here we have the control panel. But if we click Add Tools, it's not working. We have the same network error. So this password is sharing the same hash, but it's not sharing the same 4 magic bytes. As you probably could be thinking right now, the worst case scenario here is that we have to try with 128 possible passwords. But don't worry about that, because the application won't block you. You try with many passwords. Okay, so there's no problem. So now, well, here we know that the valid password in this case is the number 16. Copy the password. Paste it here. As a proof. Now here, paste the password, click OK. And now it's getting slower. It's good news for us. And here we have the control panel. And finally, if we click at Tools, it's working, and we can do a lot of stuff. We can connect to the client. We can do any backup task or restore task. We can copy any file of the file system. As you can see here, we can connect to the hard drive, get any file, and so on. So, thank you. So, with this, we can have full access to any remote client, sorry. We don't need man in the middle or anything else. We can backup or restore any file, for example, restoring an executable, sounds good, right? We can execute any executable after any backup restore task as a feature of the application, so we can have remote code execution because of this feature. And of course, we tried with more complex passwords and test. We tried with this super secure password, as you can see here. And this is the hash of this password, and in this case, the valid password will be the first one. Okay, now we are going to talk about the other backup software. It's the Novosoft Handy Backup. It's a backup client server widely used by some famous companies, such as Siemens, Motorola, Royal Canin, of course. I like dogs. And there are no public vulnerabilities in this product, at least during our research. So we decided to test it using protocol fuzzing, and then we found an authentication bypass and a curious permanent denial of service. First will be the authentication bypass. The first step, like always, will be understanding the communication protocol. It's GEOP, the protocol is GEOP, and Wireshark has dissectors for this protocol, so it's a good news for us.
A summary GEOP is Corba, it's Common Object Request Broker Architecture. It's created by ONG in 1991. It's a protocol like SOAP, RMI, DCOM, RPC, and it's providing interoperability between vendors and languages, so you can call operations in C++ using object developed in Java. It has many elements, you can see this, okay, but we have to focus in this protocol because it's the protocol that Handy Backup use. GEOP use header and has some ciphers, okay, there's important things there. This is the header and this is the cipher. This length has to be the same length that the below data, okay, below data in the packet. We are focusing the authentication because we love to break authentication. We pick up authentication packet and we realized that it was in clear test, as you can see in this screen.
Okay, the next step will be fuzz the authentication packet, in this case using Sully, the Sully framework. Here we have the Sully template of the authentication packet. Here we have the authentication packet. And as you can see here, we have here one sizer, okay? But what do we miss here? Well, the GEOP protocol in this software uses several sizers. For example, in the authentication packet, it uses a sizer for the username, for the password, and so on. And as you can see here, we are only using one sizer. So we made a mistake, and we found the vulnerability. I mean, if you try to configure all the sizers right, you won't find the vulnerability. As you can see here, we were fuzzing, and we were inspecting the requests and responses in the Canopy log, and the responses from the server were always 68 bytes. But as you can see here, we have this interesting one with 208 bytes. And if we look at the packets, we can see that the username and the password are all zeros, and we have a valid session in the backup server. It's actually a session of the user number 6. So as you can see here, fuzzers are not only for crashes. Here we have this pretty self-explanatory example. But another one, maybe Heartbleed. You know about this, of course.
Okay. Some requirements. We don't need mine in the middle. We use the graphic client in order only to solve the exploit better. We only have to change the authentication packet by our authentication bypass packet. Let's see how it works. Okay, this is the authentication bypass packet. This is the nodes of handy backup. Okay, and we are going to use in Canapit a node that you can intercept all the requests and all the requests to the server. We're going to restart in order to work. And we're going to connect to the server. Okay, this intercepts all the packets. This is not important packet. Okay, but this is the important packet that contains authentication. So we only have to change it by our authentication bypass packet. So copy it and paste it. Okay, we click OK. Okay, here you have, this is the valid session. In this case, URL3. We have disabled the editor in order to not intercept anymore these kind of packets. And we're going to see how this works. We have to wait a bit. Okay, here you go. You have full access to the backup server. I go a bit faster, okay? But you can list the cpath and do so many things. Okay, so you can do many things with this vulnerability. You have full access to the backup server. You can make backups of all installed clients, restore of all installed clients, modify binaries, execute command after tags as a feature of the application, as you can see in this screenshot. And finally, we sold it to Bayonne Security. As a proof of concept, we made a Python exploit in order to list the C, just only a proof, because we have to simulate all the J communication protocol and parsing all the response, and it's a bit tedious task. So we're going to see a quick demonstration. Wait a minute. Okay, this is the proof. We're going to execute it, but first of all, we have to show the exploit. Okay, this is all the lines that we wrote. Okay, this is the authentication bypass packet that we have to send first of all. All the requests and response that we have to parse and send. And finally, you can change this letter, okay, by another letter in order to show another directory, another path. And we're going to execute it. Okay, I'll go a bit faster in order to show you. We're going to open the C path as a proof. And if you look at that, we have the file test, okay, and the file test in the C path. So we are listing the disk. This is an important thing, okay? This is Canopy log, and you can see all the requests and response that you have to parse and send. And the important thing is this packet, okay? The 208 length. Remember the authentication bypass packet. And that's all.
Okay, the next vulnerability will be the permanent denial of service, and the last one. Using protocol fuzzing, we found this vulnerability, modifying the name of a task, putting a really big task name in this case. And when the application tries to start, it always crashes. Of course, it's not an exploitable crash, but the only solution, the only way to solve this issue is uninstalling the application. There is no other way, so it could be really, really annoying. The last demonstration video of our last exploit, again, we don't need my in the middle. We can brute force the user number, account, and the task number. We'll see in the demonstration video what's this. And we can have the user numbers and task of the server sending a geo packet without any authentication. Again, we will see what's this in the video. And finally, we just need to send the malicious packet. Let's see how it works. Okay, here we have the server. We have this task sample created as an example. And we'll use, again, Canopy. In this case, we will use the network client of Canopy in order to send the packet. And here we have the packet. And as you can see here, we have the task name, which is really big with a lot of A's. And here we have the user number, and here in the right, the task number. And these values has to be right, okay? So we can brute force these values, okay? Or we can send a geo packet to the server without any authentication, and the server will give us all the user numbers and the task numbers. So we can do both things if we want. And then you will send the packet with the network client. And here, in this case, the server is responding with an error. And that's why, because the user number in this case is not right, as I was saying. So now we know that the user number is 18. We change the user number, and remember that we can brute force these values or get these values. And now the server is responding with an OK, and now the application, the graphic interface is trying to fetch the task name, and it will crash. And if you try to open again in order to connect to the server, it will crash, it will crash, it will crash, and again, and again, and again. And the only way to solve this is uninstall the application, so it could be fun.
Okay, so as a conclusion, hacking backup server or backup client could be very dangerous. We found several authentication vulnerabilities in other products using the same techniques. Math sometimes can help us to go further. Fuzzing and reverse engineering sometimes let us to find more things than doing source code analysis. Fuzzing is easy and works, and it's not only for crashes. Remember handy backup authentication bypass. It spends for us 10 minutes. Probably if you use source code analysis, it could spend more time. Break authentication by clear backup or backup server sometimes let us remote code execution because it has this as a filter. And backup servers should have more security because they are so critical, at least in our opinion. So thanks for our hacking team, our math guys. Special thanks to Hacking Paris, to my girlfriend, and family and friends. So
Thank you.
Questions?
Thank you, guys. Is there any question? Yeah, and it's not exploitable. Well, it was 9 months ago, I guess, or 8, 7. I'm not sure why. If you want to know why it's not exploitable, we can check it later, but I don't remember right now why it's not exploitable. You're welcome. I think that's it. Yes, we have another. Leila, here.
It appears that you sold one of your vulnerability to Beyond Security.
Yeah.
Is it possible to have an idea of the amount of money?
Woof. I'll tell you later.